Alrighty, friends, it's Unit 2. Unit 2 is all about differentiation, how it happens, a little bit of why it happens. And so today, our focus is on a rule that's very familiar to us. It is the quotient rule for derivatives. Those familiar with our song will recognize that as the first word in the song, and if not, you will recognize it before too long. The quotient rule for derivatives says that if you have the derivative with respect to x of some function that is a quotient of two functions, call them u and v, that is v times du dx minus u times dv dx over v squared. Very catchy, very easy to remember. Basically, we sing, it's the bottom times the derivative of the top minus the top times the derivative of the bottom. For the rest, you won't be scared. It's all over the bottom squared. This is calc, this is calc, this is calc. Again, it happens for a reason. That reason is so important that we will do it in purple calligraphic pen. The proof is very straightforward. We're going to take a limit as h approaches 0 of f of x plus h minus f of x over h. And you may say to yourself, why did he leave that space? Well, because I know what's coming. Ha, 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 ha. As it stands, we can't throw h equal to 0 in, and we can't do that for a very simple reason. We would get 0 over 0, and that's just weird. So we end up working it out in a similar way to what we did with the product rule. We are going to subtract and add the same quantity, and that quantity is u of x over v of x plus h. U of x over v of x plus h. In doing so, we have not changed the value of anything, which is very useful. Sorry, that's going to annoy some folks. We haven't changed the value of anything, but we do have something we can use now. Because if we take a look at the stuff on the left is 1 over v of x plus h times u of x plus h minus u of x over h. On the other side, we've got this other thing here where the u of x comes out. And then we've got, what have we got? We've got a mess is what we've got. If the u of x comes out, we've got u of x over h. No, we don't. 1 over v of x plus h minus 1 over v of x. So here's the craziness in all of this. If I look at the thing on the left as h gets closer and closer to 0 appears to be 1 over v of x times this thing, which is the derivative of u with respect to x. Right? The thing on the right, this thing, well, I should go smaller with that because u of x is u of x. This thing, I want to know what that is as h gets closer and closer to 0. Well, I'm looking at v of x minus v of x plus h over v of x v of x plus h. That's my thought there. And there's an h in the mix that we dropped out. There's an h in the mix that we dropped out of there. Sorry about that, folks at home. So what have I got? I've got u of x over, magic pen, this thing. This thing, as h gets closer and closer to 0, gets closer and closer to v of x squared. That's what's going on your bottom. And then what's left? What's left is the h and a v of x plus h minus v of x, but it's reversed. And since it's reversed, the limit of the green quotient is the negative of v prime of x. So what happens? I want to combine those things with a common denominator. That common denominator is v of x squared. To get that, I've got to multiply here by v over v. So what have I got? I've got bottom times derivative top minus top times derivative bottom over bottom squared. So your quotient rule does work, and it does work for a very straightforward reason. It is an application of definition of derivative. Now, do you have to figure out how to derive that? No. For your purposes, you have to know that there is a derivation, that it does come right off the basic definition. You have to be able to see, oh, look, that thing really is a derivative. Those are the things that you have to be able to do. From a much more practical standpoint, you have to be able to do this. You have to be able to differentiate y equals x minus 4 over x squared plus 4. You have to be able to do that. You have to be able to say it's the bottom times the derivative of the top minus the top times the derivative of the bottom. Now we remember the derivative of the bottom from yesterday, that's power rule. 2 comes out in front and the power decreases by 1. 4 has a derivative of 0. We covered that yesterday. For the rest, you won't be scared. It's all over the bottom square. This is calc, this is calc, this is calc. And that simplifies very nicely. I think you'll find that that simplifies just like so. There's no reason to expand the brackets on the denominator, no reason whatsoever. If I can. Yep, that's right. I'm skipping right to example 4. Find the equation of the tangent line to y equals x plus 10 over x squared plus 4 at 3, 1. Equation for the tangent. How do we do that? Well, first we need a slope of the tangent. Because see, here's what's really happening. The tangent line looks like this. Y minus y1 equals x minus x1 multiplied by the slope. That's going to be the slope. How do you find slope? You take the derivative at x equals 3. So how are we going to do that? We're going to say it's the bottom times the derivative of the top. And we remember that the derivative of the top is the slope of the line x plus 10, and that's 1, minus the top times the derivative of the bottom. And in a similar way, the derivative of the bottom is 2x. For the rest, you won't be scared. It's all over the bottom square. This is calc, this is calc, this is calc. That notation means we evaluate that expression at x equals 3. And if we evaluate that expression at x equals 3, we get 3 squared plus 4 times 1 minus 3 plus 10 times 2 times 3 over 13 squared, and that happens to be negative 5/13, and that's exactly what you write there, and you do not simplify. And the reason you do not simplify is because you will get it wrong. I could do more examples, but I'm going to save those for tomorrow. One other thing that's a part of this lesson is the idea of a little bit of vocabulary. When we talk about y double prime is the derivative of the derivative. It's called the second derivative. If you're using Leibniz's notation, it's dy prime dx. It's the derivative of y prime with respect to x. Leibniz would have written it as d squared y dx squared. That is Leibniz's notation for the second derivative. That is not the derivative squared. Is not. Is not. Is not. So in a similar way, y triple prime is the derivative of y double prime, is the third derivative. Those are all equivalent notations. When we get beyond the third derivative, older people are going to write Roman numerals. Younger people are going to write regular American numbers in parentheses to indicate the fourth derivative instead of y to the fourth power. So what happens when I want to find y double prime if y is x plus 2 over x minus 4? What if I want to find that? Well, that's not bad. Well, y prime first. It's the bottom times the derivative of the top minus the top times the derivative of the bottom. For the rest, you won't be scared. It's all over the bottom square. This is calc, this is calc, this is calc. Your denominator is x minus 4 squared. Your numerator is x minus 4 minus x minus 2. That's negative 6. So then when we go to find y double prime is the derivative of this. So it's the bottom times the derivative of the top. That drops minus the top times the derivative of the bottom. Now, we don't know how to take the derivative of things squared yet, so we actually right now have to do that thing. The derivative of the bottom is 2x minus 8. For the rest, you won't be scared. It's, oh, I wasn't scared, I just got it wrong. It's all over the bottom squared. When you square something that's squared, it goes to the fourth power. This is calc, this is calc, this is calc. Anything times 0 drops out. This thing right here is 2 times x minus 4, which is fortuitous because that allows some cancellation. And we say, I got this, you got this. Done. So from your perspective, what do you have to know? You have to know that there is such a thing as the quotient rule. You have to know that it comes from somewhere, and you have to know how to crank out derivatives of quotients because they're always out there. I'll have some further examples when we get to class tomorrow, but that's the basic idea, and I hope this was a good refresher for you. We'll see you tomorrow.